now what I want to do next is to talk about the connection between the Bayesian classifier and also the linear regression classifier. So to do this connection, I want to look at the loss function. Okay, so previously we were doing the estimation, now we're doing the classification. So I want to look at the loss function, and I want to send the number of training samples to infinity. Okay, so that means you have infinitely training samples. Now the reason of doing this is that you don't want to get trapped by the finite sample situation where there is another layer of complexity or error coming from having not enough samples. Okay, I just want to look at the model level, intrinsic model level, and not the sample level. And that's why I want to say n going to infinity. If I say n going to infinity, then this is what? This is the average. The average can converge to the expectation of this square loss. Okay, so the average will go to the expectation. Now the expectation is taken over x and y because there will be some distribution, a joint distribution between your input data and also the label. Something that I don't know, but there should be some distribution. Okay, so now if you want to minimize this loss function, okay, this is a finite loss function. Approximately as n going to infinity, you are really just minimizing this expectation of this 2-norm square loss. And so now, if I know the distribution of x, I know the distribution of y, then I should be able to evaluate this joint expectation, and then take the derivative, set it to 0 with respect to w and w0. I should be able to get some numerical, analytical answers. If I can do that, then I will be able to perhaps draw some connections with the Gaussian, Bayesian decisions. Okay, so here is a main theorem that we can look at. So under what condition will this linear regression equals to your Bayesian decision classifier? Okay, classifier. The condition is this: the likelihood is a Gaussian. All right, this is something that we should expect. It be Gaussian with a covariance matrix sigma. Okay, it doesn't change with I. So both both classes, they will have the same sigma. And what else? Well, the prior is uniform. Okay, so prior of getting +1 and -1, they're uniform. And then the number of training samples is going to infinity. Then some magical thing will happen. The magical thing is that your W is given by this equation. And then your W0 is given by that equation. Okay, so now, remember that we are solving a linear regression problem. We don't have access to all this mu1 and mu-1, etc. Okay, but if you put a Gaussian model, okay, on your x and y, then you can show that the linear regression model parameter, so these are returned by your linear regression, they will take this form. It actually matches exactly with your Bayesian decision rule. Okay? In other words, under these conditions, the linear regression is the same as the Bayesian. Now, if these conditions are violated, then your linear regression is doing something else. It's not returning you the Bayesian decision rule. Now, is it a good thing? Is it a bad thing? If your underlying model is indeed Gaussian and your linear regression is not, okay, so the conditions they are not satisfied. It could happen that the two classes, they are not 1/2 and 1/2. It could happen that they have two different covariance matrices. Then by solving a linear regression, and if your underlying distribution is indeed Gaussian, then your linear regression classifier is not good. Okay, it's not good because your optimum classifier, the minimum probability error classifier is defined by the Bayesian. If you have a linear regression result that is not the same as your Bayesian, and if the underlying is indeed Gaussian, then you are screwed. Okay? If the underlying is not indeed Gaussian, then you may be good. Okay? Because the Bayesian, the Gaussian is not solving the problem. Okay? So, the derivation of this result can be found in the appendix of this lecture slide. I will just very, very briefly comment on what are the algebraic tricks that you want to read as you look at the proof. Okay, so this is called a sketch of the proof. It's not a proof. So I'll go over it very quickly. So you have a likelihood function is Gaussian with equal covariance, and so you can calculate these two likelihood functions. One is this Gaussian, the other one is the other Gaussian, and then you have equal prior. So what happens is that you can take the derivative with respect to w and w0 for this loss function. This is really the loss function when the number of samples go into infinity. You take the derivative, and then you get these quantities. And so as soon as you can evaluate as soon as you can evaluate this expectation of x transpose, expectation of x, expectation of xy, put it in, you should be able to get the w and w0. Okay? And this is a linear equation. So in principle, you should be able to find out the solution. Now, the following steps, they are nothing but just tell you how do you evaluate expectation of x, expectation of xy, expectation of x transpose. Okay? So it involves some calculations, and the calculation is just about conditional expectations. So once you are familiar with all these steps, then you just follow the derivations, you will be able to get to the solutions. Okay? Then at the end of the day, you can show that this will give you a quadratic term, and then these will give you the linear terms. Plug in, set it to 0, you can show the main theorem. Okay, so the main theorem is here. Okay, so you will be able to get these two quantities. Proof is in the appendix. You're welcome to read them. I'm not going to go through them now. Okay. I want to spend more time talking about the implication, because the algebra you can read it by yourself. The implication is the following. If you look at the theorem, condition 1 says that the linear regression will match with the Bayesian decision rule when they have the same covariance. That's very important. So if the two classes, they have different covariance, then your linear regression is not solving the right problem. And so Bayesian allows different covariance matrices, but then for linear regression, you must assume the equal covariance. Okay. And also, what else? Well, then you look at criteria number 2. The criteria number 2 says that the prior are uniform. So the prior distribution says that you must have half chance of getting class 1, half chance of getting class 2. If you have 90% getting class 1, only 10% getting class 2, then linear regression may have some issue, as predicted by this theorem. Okay. What else? If the training sample is not going to infinity, then you will have some problem which is not clear yet, right? The problem will be that when you solve the linear regression problem, you're solving a finite scale least squares, versus your Bayesian decision rule, assuming that you have a lot of data. Your Bayesian decision rule, the means and covariance, they're good, right? So you may not get there yet. So I want to show you a set of very simple experiments that even you can go home and program it on Python, and you can verify whether my experience is correct or wrong. Okay, so let's look at those. Now, when will linear regression go wrong? Okay, so I have a few case studies here. Case 1 is that when the classes, they are intrinsically unbalanced. All right. So what do I mean? It means that first of all, here you have a very, very, very big variance. That's class 0. This is class 1. Okay. Class 0, you have a big spread. Class 0, you have a big spread. Class 1, you have a very, very small spread. Okay. Now, okay, so, and then if you try to fit the data, okay, so what are the blue crosses? The blue crosses, they are a lot of these samples. Okay, so let's say you have drawn a million of these samples. So they are the underlying, blue comes from the true distribution, and then you have a lot of these, okay? The orange circles, they are the finite samples. Okay, so you have a big training set, but then you're using a small portion of that. Or you can think it as you have a very big population set, but then you're using a small set for training. Okay, so the orange circles, they're the training set. Okay, so now when you try to fit the data, you're trying to find a red line that can go through all these orange circles, because you don't have access to the population. You only have access to the training set. So you're drawing a red curve. Now, because you're using linear regression, and in this case, unfortunately, one class you have a very, very big variance. The other class you have very small variance. And therefore, assumption 1, condition 1 is violated. Okay? So let's see what happens. To Bayesian, it doesn't matter. Why? Well, the Bayesian says then, okay, you have a big covariance here, small covariance there. I will just go to case 3, the arbitrary covariance situation, right? And then we know that it's going to give you a quadratic classifier. Oh, okay, by the way, by quadratic classifier, you can visualize it as here is a plane, and then you can draw a quadratic equation there, okay? And then when you set a cutoff, okay, above this value, you can declare it is a +1. Below this value, declare as -1, right? So the discriminant function is indeed a quadratic function. The hypothesis function, the decision boundary that it creates, can be something like this. Okay, so that is the power of the Bayesian decision rule, which can go to a quadratic case. And in the quadratic case, we have shown that Bayesian is optimum in terms of the error probability, and therefore it is the best you can ever get. Okay, so the black line is obtained by using all these blue crosses. That's the ideal, that's the best possible Bayesian classifier you can ever get. Okay, anything that is different from this black line is considered as not good. Okay? Okay, so the red line is one. The red line is trained based on all these orange circles. They're the finite sample trained classifiers. And then you ask, what is the hypothesis function for this given discriminant function? So since this ranges from 0 to 1, then you set a cutoff here. Then the hypothesis function will be 0, and then it will go to 1 at 0.5, okay, at this point, okay? So this, my hand-drawn line is the classifier returned by the linear regression. The solid line print on the paper is the ideal, the best, minimum probability error rule returned by the theory, okay? And you can see that there is a pretty big gap between the two. Okay, that is exactly because condition 1 is violated. So you ask, can you give me some intuitive reasoning why this is happening besides going through the equations? So you can look at this diagram. Okay, you can look at this diagram. Here you have two classes. One class spread out. The other class is concentrated somewhere. Okay? And then what is the linear regression? The linear regression is nothing but the sum of the squares, and then that's the loss function. And this is a very democratic a country for these squares, okay, for linear regression. Everyone has the same vote, okay? And then if these guys, they are really, really loud, like in any kind of meeting, faculty meeting, okay? If someone is really, really loud, then the person is going to dominate that meeting. That's what's happening in this regression, okay? So these are the quiet people. These are the really, really loud people, okay? And of course, the loud people, they will dominate the meeting. And so you're putting a lot of emphasis to minimize your error with respect to these, right? And then once you try to make these people happy, of course you are going to make these guys unhappy. And then you're saying that, never mind, their voices are not very loud, so let them be unhappy. Okay, this is what's going on in this regression setting. Okay, and that's why when you have a problem like this, you have a wide spread for one case, and then a very narrow spread for the other case. Condition 1 is violated. Your linear regression is going to fail. By fail, I mean that I don't mean that you are not able to get a solution. You can still get solution. You can still get something. It's just that your classifier obtained is not optimal relative to the minimum probability rule. Okay? All right? And it will still work. Okay? You can still put into your autonomous car. It will still run. It's just that the error that it's going to make is higher. Okay? Higher when the underlying true distribution is indeed Gaussian. If the true underlying distribution is not Gaussian, it's actually okay. You just don't know. All right? Okay. So that's case 1. Case 2 is what? Case 2 is that you have all these blue dots, and then these are the ideal data points. You have a lot of these. However, when you try to train the classifier, you are going to use a subset of orange circles. And in this particular case, you have very, very few in one class. You have some on the other class. That can happen when you say that here you have 90% of the samples they're occupying here, and then only 10% of the samples they're occupying there. Okay, so that's about condition number 2, when your prior distribution is somewhat unbalanced. Okay, and so if you have this case, then what will happen to the Bayesian? Well, the Bayesian, you do have a knob to tune this prior distribution so that you can mitigate a little bit. But another issue that hasn't been addressed is that if you really only have 2 circles here, then remember that in Bayesian case, now Bayesian doesn't have access to the blue dots. This is just the ideal line. Bayesian, you're estimating the mean. You're estimating the covariance. If you have very few data points here, your mean and variance, they're still not good. Okay? So, if that happens, then I would say that Bayesian performs equally bad. Okay? Because you don't have enough training samples. This is not about your distribution. That's more about your number of training samples. If they are few, both will be suffered. Okay? So linear regression is of course bad. That is, the same game, but then with a different perspective. Here, you have a lot of people over there, but you only have a few people over here. Okay? And so you're spending majority of your effort trying to make these people happy. Okay, so now we can also ask, well, okay, will regularization help? Indeed, regularization helps because when you don't have enough training samples, then this Bayesian approach will help you find a better mean and help you find a better variance. Something that the linear regression doesn't have unless you put the ridge regression kind of approach into your model. Okay? Now, the last case, and after that we'll be done. Okay? So, the last case is the outlier. If you have an outlier here, then what will happen? Bayesian case, I'm sorry, it also failed because you're taking the mean of these. Okay? So the Bayesian will be suffered. For the linear regression, of course you will suffer because you have a really, 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 really bad guy. Okay? So both of them will be bad. Okay? Now, so, there are a lot of readings. Again, these are actually pretty long if you read the textbook, so I only put a few here. There are a lot of discussions about the Bayesian decision rules and also the linear regressions. The connection seems to be I wasn't able to find anything on the internet, so that might be something interesting to read by yourself from our own lecture material. And also this kind of connection, these kind of case studies, I think it will be useful if you really understand that, because that really tells you the very, very subtle differences between these classifiers. Okay, so we will resume our class next week, and then we will talk about logistic regressions.